Okay. Oops. Don't want that. I guess that's fine. So I'll be helping out after class, so we'll be talking about red-black trees today. So in order to help you out with Project 2, I'll be around after class for some office hour type meetings. Yeah, I'm glad that the project got extended. Let's check when the new due date is. I forget exactly. Instructor Lounge. So, oh, I think is it on the project website? Let us check. Oh, it's been given an extra day. Oh, I thought I'd been given more time. 1 extra day. That's all. So I guess I'll be helping out today and tomorrow. Anyone who needs to get things done, we'll make sure that we get everything in by Wednesday night. Alright? So, yep. Okay. Cool. Alright, so let's get back into red-black trees. Because, you know, we'll talk about self-balancing trees and all that. So, okay. So remember the rules for red-black trees, right? So the unstated rule is that a red-black tree is a binary search tree, right? So it's a binary search tree. Red-black tree, I'll spell it all out, is a binary search tree. Let's talk about some other rules. What other kinds of rules are there? The first rule is just every node is either red or black. That basically just ensures that we have no nodes that have any kind of, there's no mixed colors, there's no white nodes, there's no green nodes, there's no yellow nodes, there's no purple nodes, there's nothing like that. So in deletion, there's sometimes a double black node, but that's kind of like an accounting trick that we use until we get back into a red-black state. So whenever you have a double black node, that means that you're in a deletion and you're not actually, the thing that you currently have is not yet a red-black tree. So, okay, the root is black. So it's a moderately, yeah, it's important. It's important just because we're always going to be inserting red nodes. And so if a node is red, its children must both be, I'll say this, its children are not red. Basically what that means is either its children are black or null pointers, which are also considered black, but I'm going to make the distinction just because I think it's kind of nice to say these things more clearly. Sometimes people try to make it a little too tricky and say things like, oh yes, both of its children have to be black, but then does that mean that you need 2 children or not, or whatever? So then oh, that was rule 4, whatever. Actual rule 3 was every leaf, and now of course they say every null pointer is black. So that's rule 3. And so we need that for certain conditions, and I'll show you those conditions when we get to it. So, okay. And then for each, here's the last rule. For each node, all simple paths, which just means paths down the tree, meaning don't go back up, from the node to descendant leaves contain the same number of black nodes. And so what this allows us to do, right? So what this allows us to do is that this rule allows us to talk about the black height of a node. And because we can talk about the black height of a node, what it means is that the black height of a node is the same down all the different paths. So you know how for like an AVL tree, AVL height of a node is equal to 1 plus the maximum of the AVL height of the node dot left and the AVL height of, I guess I'll use HT, of node dot right, and something like this. So this is the AVL height property, and this is basically how heights are computed in trees. But the good news about red-black trees is that the red-black height of a node is equal to 1 plus the, let's see, yeah, instead of calling it the red-black height, let's just call it the black height. It's really just 1 plus the black height of the node dot left, right? And it doesn't matter, and you could say, well, what about in the node dot right? Well, it's also equal to the black height of the node dot right. So you don't have to take the maximum because they should both be identical. If they're different, then that's a problem. And then, so this is the black height if, right, if the node itself, like if node dot color is equal to black. And if the node is a red node, then it's all basically the same, except that the only difference here is that it's 0 plus that, right? So you don't add 1 on when it's just a red node. You only add 1 on when it's a black node. And so you might be thinking, like, how do we actually keep track of all this stuff? And the answer is, the secret answer is we don't actually ever compute any heights in a red-black tree, right? And the reason is a red-black tree doesn't have any, let's call it, any parameter or whatever, variable, class member, whatever you want to call it, that describes the height. Nodes, right? The only thing about nodes only know their colors. Okay, so that's basically the rule here. And so what we have to do is basically we have to argue that, I mean, we'll go through some of this, but basically we have to argue that the black heights are preserved by the operations that we're going to do within. So basically there's like insert, right, delete, find, and all that stuff, you know, create, insert, delete, find. And so basically the point here is that find is just the regular binary search tree find, so this is regular BST. It doesn't care about the colors. Delete is pretty... Delete and insert are the ones that are really kind of bad. So let's go over a bit about insertion now, okay? So let me create some... interesting. I didn't realize that it would be... Okay, there we go. So now we have a red node and a black node. Cool. So really there's, as I said before, there's like 2 different cases of insertion. Let's call it, actually there's 3 cases, but let's break them down into cases 1 and then case 2A and 2B. And the reason why I break them down into case 1 and 2A and 2B is case 1 is that the uncle is red. And then case 2 is the uncle is black. And so that will really, and you might be asking, the uncle of whom? So let's draw out some kind of tree structure here. So let's say we have, let's look at this tree structure right here, okay? And let's see, oops. So basically, if we have this tree structure right here, and say this is the root of the tree, and it has 2 children, so we're in this condition here, then the point is that, is there a way such that the root can be, so that's the question that I guess I have for you guys, is there a way to make the following work, right? This work. And what I mean by this is, remember that red nodes can't have red children. So if I ask you, is this a red-black tree? Your answer is, well, there's some red nodes and there's some black nodes, but no, it's not, right? Definitely not. Right? So just having red nodes and black nodes does not make you a red-black tree. The property of being a red-black tree is determined by your following the rules. And the primary rule that we're going to break, right? So I guess half the time we're probably going to break the root is a black node rule, but the point is we can always just recolor the root black. So we can always recolor the root black. And why can we do that? That's a good question. Why can we always recolor the root black? And the answer is, right, because it doesn't, well, it does affect the black height. It does affect the black height, but it affects the black height for all nodes, right, under it. So basically, if you start at the root and you go down, you'll know that if the root is black, you have to add 1 for the root. If it was red, you would add 0. But the point is, like, who cares? Because it's going to be that 1 plus the rest of the path all the time. So you just get 1 plus the rest of the tree. And so it doesn't really affect... It shifts everything up by 1, but it doesn't really affect the red-blackness of the tree. Okay. So we can always recolor the root black. So that's a trick that we're going to use. Let's put that in our little repertoire of tricks. And so if this is the tree we start with, let's actually mess with this tree and try to make it into a red-black tree. So there's 2 things we can do. We can either rotate or recolor. And so let's try to recolor first, right? So what happens if we make this node black and say this node red? Well, then you say the root has to be black, right? That's one of the rules. So we have to keep this node black. But then what do we see here? What we see here is that the black height is not the same, because here, let's not add the black height of the leaves of the null pointers. Let's just say the black height in this direction, right? The black height here is 0 along this side. But then the black height over here is 1, right? Over here. And then you notice that this breaks our rule, because we're going to have to do 1 plus the black height of both of these, but the point is that these both need to be the same for it to be a red-black tree, so that's not possible. So, okay, so it's going to either be 1 plus 0 or 1, right? So technically, the black height here is going to be 2 if you define it as the max, like the standard height. But the problem with defining it that way is that, well, you can define it that way. There's no problem defining the black height that way. The only problem here is that it just isn't a red-black tree. Okay, so let's make this one red, and let's make this node black. Right? Okay, same problem. Right? Except now we don't get the black height there. The black height is 1 here. The black height is still 1 here because we don't count the red node, and then the black height is 2 here, but the black height is 0 over here, so it doesn't match on both sides. So this breaks rule 5. Right? So they can't both be red. They can't all be black, right? And they can't be any combination like this, right? You can't have an alternating. So none of this is possible, right? It's not possible to have this condition. None of these are possible, right? So what are we going to do instead, right? The only thing we can do now is rotate. And, it's kind of what we wanted to do anyway. When you see a tree structure like this and you think AVL or some other kind of self-balancing, you think to yourself, I want to rotate this. So let's rotate this. I'm going to do a rotation, this way. And then I will do something like that. So this is the rotation we're going to do, right? We're going to rotate this node up. So let's do that rotation. So the black node will come down here. The red node comes up to be the root. And that's it. Okay, so is this a red-black tree? Well, it's a more balanced tree, right? It's more balanced, but it's not. Not red-black. And the reason why is because it still violates two of the rules, right? The black height isn't the same in both directions. Here the black height is 1. Here the black height is actually 0. So it's not red-black because the black height's not fixed. And a red parent still has a red child. So how to fix this? How to fix this, right? Well, the rotation fixed this kind of imbalance, but we still need to fix the coloring. So what we do is we flip the colors of these two things. So what we're going to do is we're going to do this. We're going to change this one to red, and we're going to change this one to black. And then what you see is that this does actually fix it, right? This fixes this condition, right? And so why did we rotate? And I tell you, it always has to do with the uncle. And so who is the uncle? Let's say that the imbalance occurs here, right? And so if the imbalance occurs here, then we would call this the parent. We call this the grandparent. And we would call this node here the uncle node, right? And so basically what we're going to do is we're going to say, because we see that the uncle here is null pointer, remember that the uncle is considered to be a black node. So if the uncle is considered to be a black node, then you do the rotation, right? Then you do a rotation. If the uncle is a red node, so let's do the case where the uncle is a red node. So let's say that we have this condition here, except now we have another node over here that's actually red. Okay. So this is a kind of balanced tree. The only problem, if we look at this condition, right, we see that here's the node, here's the parent, here's the grandparent, and here's the uncle. I guess you could also say aunt, but I don't know. I always say uncle for some reason. The uncle node. And so it satisfies the requirement that all the black heights are the same, so that's fine. Nodes are either red or black. Everything is basically fine with this tree, except the fact that there's a red node with a red child. And so that's the problem. This is the issue right here. And so because this is the issue, we have to resolve it some way. Now you see that the uncle is red this time. So there's actually a trick that we can do. Okay? There's a trick. Here's the trick. We don't actually have to do a rotation this time. And you see that a rotation wouldn't really improve our lives anyway. So if the uncle is red, so this is basically case 1. Then what we're going to do is we are going to pull the color from the grandparent down to the nodes here and here. So let's go through why we know this is going to fix a little bit, right? It'll help because, one, we know the parent is red. And you might ask, how do we know the parent is red? Why? You haven't convinced me. So here's why I know the parent is red. If the parent isn't red, then the fact that I am red doesn't matter, right? Black nodes have no restriction on their children. Black nodes can have red or black children. No rule, right? So we know that the parent is red, and we know the uncle is red. And you might ask, how do we know that? And the answer is, because that's case 1, right? If not, we're in case 2, right? So basically all I'm saying here is we know that the parent is red, we know the uncle is red. Do we know the color of the grandparent? And the answer is yes, right? Now I drew it in as black, right? I drew it in as black, but maybe I'm wrong. right? Maybe I'm wrong. Maybe it can be red. But you look at the things that we already know, and what are the things that we already know? We already know that the uncle and the parent are red, and we knew that the tree, the one thing we're going to be able to assume, right? We're going to assume that this thing was a red-black tree before I messed with it, right? By inserting the node, right? So if I insert this node, I'm going to assume everything else was in the red-black condition. If it isn't in the red-black condition, then we're totally messed up, right? We can't do anything because I promise you that the red-black algorithm assumes that everything except for the one violation is in the red-black condition, right? Is a red-black tree. So you can't just have a completely random tree and then fix it, right? So if you just have a random tree with reds and blacks and then you run some, there's no algorithm that takes you from like a random red-black tree with no color, none of the rules followed to a red-black tree. Like, there's no way to do that. You would basically just have to reconstruct the entire tree. So what we get to do here, then what I'm going to propose, my proposed solution is this. I'm going to pull the black color down to the parent and uncle, right? And let's watch that happen. And I'm going to color the parent, the grandparent red, right? So, well, okay, let's do it in two steps. First, I'm going to pull the black color down. So let's make these two nodes black. And then you'll say, but wait, Eric, you can't do that because A, and you might say the problem is if you do that, you'll mess up the black heights, right? Because imagine that this is part of a bigger tree, right? So basically what I'm saying is like there's nodes above this, right? So the black height has to be the same, and I've just added two new black nodes, one along each path. Now the black height is constant along from here down, but the point is if there's other stuff over here, then the black heights will be messed up. And so I say, okay, I got you. I agree. I can't just do that. So what I have to do is I have to push this red color up to here too, right? So, and then you say, oh, okay, that looks better, right? Now I'm happy. Now you might say, well, what if that's the root? And the answer to that is recolor it black. And then you ask, what if it's not the root? You know what I mean? So if this is the root, then we just recolor it black. But what if it's not the root? Meaning that there's more tree. Let's draw out some more tree above this. So let's say that there's, something like this. Let's say that this is a black node. I don't know. And then let's say that there's something like this, and this is a red node like this. Say we're in this condition, right? And so what you'll say is that, it's possible that we're still in violation, right? We fixed the violation at this step. So down here, the violation is fixed. Whoops, big red. So down here, the violation is fixed, right? Well, in that case, what you have to do is you have to set node is equal to the grandparent and do it again, right? And this is called the red-black fix-up process, right? Red-black fix-up. And so the answer is, what you do is then you shift the node up to its grandparent and you try again. You do everything again. And the reason why you want to do everything like this, the reason why you want to move the node up here, and then you would say, okay, now you are the parent, and the grandparent is way up there, and the uncle node is over here, and the uncle's black, and this is why you want to do it. And the reason why you want to do this is because it's possible that by pulling the color down, you've created another violation here. So basically, you're going to trace your way back up the tree doing this process. So here, you actually kind of jump over the parent. So like in AVL trees, you go right from the parent, or from the node, you might do some rotation here. You do the parent, you might do some rotation here. You do the grandparent, you might do some rotation here. And that's what you do. But for a red-black tree, at least in case 1, right? The red uncle case. Maybe we'll just call it the red uncle case. In the red uncle case, all you do, and of course now this is the black uncle case, but the point is that it was the red uncle case before we fixed it here, right? So this was the red uncle case. All right, cool. So now let's talk about the other case, right? So we know that so this is the recolor case. All we had to do was recolor, there was no rotation. Just recolor. So, now let's talk about the other cases, right? Let me pull them up to make sure I don't screw something up or whatever. But, yeah, so let's see here. So actually, the case 2 where you have a black uncle case, so you have the black uncle case. We'll call this case 2, black uncle case, okay? And so let's do this case now, right? And actually this is the black uncle case right here. So let me, so, okay. So what do we do? Let's say that we're in a case like this, where we know we need to do something, right? And so if this is the node here, right? So here's the node, here's the parent, here's the uncle. And so actually let's do the recoloring here. So I think this node should be red, this node should be black, right? And so here we have the red-red violation. Remember that we can only detect the red-red violation, so that's all we can detect. So here we're in the case where you have a node, we have a parent, and we have an uncle, and we're in this condition. Now, let's think about how we're going to solve it. Basically, my hint is that we're going to have to use a rotation. We're going to have to rotate. And the reason why we're going to have to rotate is because we've already kind of gone through the argument by why we can't recolor. And so you might say, well, the black heights don't match here. Well, basically what you're going to have to assume if you're in this condition is that, let me show you this condition, right? Assume that these nodes have children, right? And so basically what you're going to assume is that this node and this node must have one more black child, like this, to make up for this, right? So this one maybe, you know, we can maybe have this one be, I don't know. So here are some subtrees. When I draw them in as black, that doesn't necessarily mean anything. Actually, let me just draw them in as clear. That way, all you see is that they are subtrees. You don't think of them as just a black node, even though there have to be black nodes in here. But don't think of them that way, right? Think of them just as subtrees. Okay, so how are we going to do this? Well, the answer is that the red-red violation is basically it's an inline violation, right? So it's to the right. So it'd be the same thing if it was to the left and the left. And so actually the cool thing is we get to do the same thing you do for AVL, right? And so what do I mean by that? Well, I mean, there's all these colors in business going on, but how would you deal with this condition if this was just a height misbalance? Well, the answer is what you would do is you would just rotate this, right? You would just rotate this way. So what you would do is you would say, I'm going to take these nodes, I'm going to push them down like this. I'm going to take this node, I'm going to push it up. I'm going to take this thing, I'm going to put it on there. And then here, so this was the old parent. This was the old grandparent. I'll just call it grand. And then here's the other node. I'll keep it over here just because there's, you know, there's all these subtrees causing spacing issues. But anyway, here we go. And finally, here we go. So you see what we've done? We've rotated. And now you say, whoa, 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 right? You say, no. None of this makes sense, right? I did the rotation, and the colors are still bad. The black heights are worse, right? This didn't help at all. So basically, I understand, right? So what are we going to have to do, right? We're going to have to recolor a lot of things. So let's think about what all the black heights are before we do this. So the black height here has to be, say, H. The black height here has to be H. The black height here has to be H. And the black height here has to be H minus 1. And the black height here has to be H minus 1. So let's look at all this stuff. So we have H minus 1 here. We have H minus 1 here. Not H minus 2. H minus 1 there. And now we have H here, H here, H here. So are the black heights okay? And the answer is the black heights here are H. The black height here is H plus 1. The black height here is H. This is 1, 2 plus this. So this is also H plus 1. So what are we going to do, right? What are we going to do? And so the answer is we are going to recolor the we're going to do some recoloring, okay? So how do we do some recoloring? Let's try this one out, right? What if we just swap the colors here? We color the parent black. We color the grandparent red. And this, of course, I'm not speaking as the new tree structure. I'm talking about the original tree structure, right? So this was the old grandparent here. And that's why I'm just continuing to call it the grandparent, even though now it's the right child or the left child of the parent and blah blah blah. So I just won't. I want to keep the same language. So has this fixed everything? And the answer is. So you say, okay, did this recoloring? So we swapped the old parent and grandparent colors, right? Or really what we did, the secret is actually what we did was we colored parent got colored black and grandparent got colored red. And remember again, this is the grandparent before the rotation. So now that we've done that, let's check all the heights, right? So this way we get 1, 1, H plus 1, 1, 1, H plus 1, 1, 1, and remember how I'm counting. So if it's a black node, I count it. So this will be like 1, 1 because this is red, 2, right? H minus 1, so 1, 2, that'll be H plus 1, 1, 2, H plus 1. And then here what we'll get is what? 1, 1, H plus 1. So all the black heights now are H plus 1, right? They're all H plus 1. And so what we've done here, right, is we fixed it. Right? So that's not bad, huh? That's pretty good, I think. Okay. So there's one case we haven't talked about, and it's actually just a case 2 again, but you might say, well, this is the straight line AVL answer, which was a rotation. What do I do if I'm in this condition, right? Let's do this business here. Come on, give me. Can I move you? Yes. Okay. Thank goodness. Okay. What if I'm in this condition? And let me try to make this. Let's put this over here, and then let's put this. Let's put this like here. I keep it far out just so that it, doesn't mess with us. Okay. So now this is the last condition, right? Because either, right, you agree, if every node is red or black, either the uncle is red or black, yes. If the uncle is black or a null pointer, then you do this stuff. If the uncle was red, then you do the recoloring stuff. You just recolor, you don't rotate. So, okay, so what do we do in this case? And you might say, well, I don't know. It's hard. But I do know, right, that in the AVL tree case, I do a zigzag rotation, right? And by a zigzag rotation, what I mean is that you would first rotate this little McDude, you'd rotate him up, right? And then you would do the other rotation once you had the straight line condition, right? So first you put it into this case, and then you do the same thing. So let's do that, right? Let's see if that works, okay? So first let's do the zigzag rotation. Right? Zigzag time. Right, this is an experiment. We don't know if it's going to work. It'll work. Don't worry. But say we don't know it's going to work, right? Say we're just afraid. And so here what I'm going to do is let's move this down here. So this is the parent. This is the node itself. What do we need? We need this guy over here now, right? We need to prune him. And then this one, I'll just relink like that. This one I'll put up like this. And what's happened? So this is the node now, right? And this is the parent. And voila, right? And you say to yourself, but Eric, same problem, right? Nothing is fixed, right? Nothing is fixed. But my argument is, I say, we didn't make it any worse. And in that we're doing good, right? We haven't hurt our case. We haven't made things actively worse. And now this is a case 2A, right? We're still in the black uncle case. We'll call this part up here, we'll call this a case 2B, right? It's still black uncle case, but it requires a zigzag. So it's black uncle zigzag, right? And we'll call case 2A black uncle straight line. Okay? So there's 3 cases. There's black uncle straight line, black uncle zigzag, but the thing is that zigzag case gets us to straight line case, right? And so that's great, because now we know what to do, right? We're mathematicians now. We say, at this point the problem is solved, right? Like, it was a hard problem, and you might think, man, I don't understand all the details of how we solved it, but you can go back over those details. What you do know is that if you kind of sort of believe me, we did solve the case 2A, so there is a solution. And the solution was you rotate against the direction of the imbalance, and so you push all this stuff down. You pull the node up like this. Let's copy paste this so I don't have to redraw it. I can be lazy. There we go. Now this is the node here. This is the grandparent. We have to put what was the node's left child, this is the same thing. This is all just rotations, right? This is all just rotations. And now we can connect. I'm not even going to move it. I'm just going to connect it up like that. Okay. And then you say, but you're still not done. But I say, but this, we haven't finished the case, right? The case says to exchange the colors of the grandparent and the node. And so what we do is we say black, red. And now are we happy? Are we happy now? And the answer is height h plus 1, height h plus 1, height h plus 1, height 1, 2, h plus 1, height 1, 2, h plus 1. Right? So at this point, what we get to say is, yeah, we did it. Right? And basically, in all cases, right, when we do these rotations, you see that this does fix the black height, right? And so, what else should I say? What else do you notice about case 2 here? So there's an interesting thing about once we do this, I think there's kind of an interesting thing that we notice, which is that once we make this coloring, is it possible that we're still in a red-red violation anymore? And the answer is no, right? Because the new node here, whatever node ends up at the top is always black. So it doesn't matter if it's parent, right? If sitting above it, right? We don't care if it's a red node sitting above it or a black node sitting above it, right? It could be red or black, and we don't care. And the reason why we don't care is because this is a black node, and this red node is allowed to have a black child. So as it turns out, once we do a single rotation, right? Or I shouldn't say that. Once you do a single case 2, either 1 or 2 rotations, we're done, right? Because we'll never find another red-red violation. So in the red uncle case, where we find the red uncle and then we recolor, then what you have to do is you actually have to step back up the tree and keep going, right? But if you end up in a case 2, that's it. So once you execute a case 2, you're done. That's it. That's it. That's all. We're good. Right? Go home. So, that's the point here, is that once we do a case 2, we actually don't have to keep recursing back up the tree. So that's really cool. Okay. All right, so that's red-black insertion. And I think this is a pretty decent lecture on it. I think maybe my best lecture in 3 semesters on this. So hopefully it's moderately intelligible. Right? And if it's not, I definitely will release this thing, because now I've drawn out all the cases, and I've named the cases in a way that I feel like I've never seen a textbook name these cases the way I did. Normally they just call them like case 1, case 2, case 3, and they don't really describe what's going on, right? And the answer is that actually what we're doing in case 2 is we're just doing the AVL fix-up. And after we're done with the AVL fix-up, then we do the red-black recoloring, because here we don't have heights, we just have reds and blacks. So that's what we do, right? So you have to do an AVL fix-up in terms of the rotation, and then what you do is you hit it with some recolorings just to make it work again. And so, okay. So, yeah, let's talk about it then. I think, what do I want to do? Okay. All right, I think that's it for insertion. So I'd like to move on, and there's a fact about red-black trees. And here's the fact. a red-black tree with n internal nodes has a height at most 2 times the LG, which is log base 2, right, of n plus 1. Okay? And so you might be thinking to yourself, like, what's the point of thinking about this? The answer is, remember, the height of a tree, right? So whenever you do insertion, deletion, find, whatever, right? Unless it's a traversal. So not traversals, I guess. Traversals are always O of n, and the reason why traversals are always O of n because you have to touch every node. But imagine that, we're doing just insertion, deletion, find. You notice that insertion, deletion, and find operate the same way in a binary search tree on the way down, right? Same as BST on the way down. And then the fix-up just heads back up, and at each level adds a constant time operation, right? A rotation is a constant time operation. A recolor is a constant time operation. So, like changing a node from red to black is O of 1. Rotating on a specific node, yeah, it's like 6 or 7 lines to do that piece of code, but it's always O of 1 because you feed it into the function. There's no for loops, there's no recursion in the rotation itself, right? No for loops, no while loops, no recursion, hardly even any if statements other than just checking for null pointers, right? So basically this thing is just real constant. It's an extraordinarily constant time, rotation is. And recoloring is also really constant time. So basically, insertion and deletion and find are all O of h, right? Where h is the height of the tree. Now, you know that h is some function of n, right? You know that h is some function of n, but the question is, what function, right? If it's a linked list, then O of h is equal to n. So that's, right? So that's no good, right? That would produce some bad times. What we want to show is that this, that the red-black algorithm, that the red-black tree properties force us to have O of h equals O of, I guess really, the 2 gets absorbed into the constant c, so I can really just say log n, right? You might be able to, the plus 1 is just a little bit of a correction factor, so I wouldn't punish yourself too hard on the plus 1. Also, whatever. You can even say plus 1 if you really want to, but it doesn't, like, that's definitely missing the point. The point is that that this is what we want to say, okay? And so naturally what we're going to do is we are going to, so I'll just put this up here. Traversals are always O of n, and then let's get into the fact about red-black trees. We want to show that this is the case. Now, if I tell you that a tree with n internal nodes has a height at most 2 log n plus 1, then we know we're good, because we know that the insertion time is log n, we know deletion time is log n, we know find is log n, and of course I haven't taught you deletion, and I might not teach you deletion. I'm not sure. We'll think about whether to teach deletion or not, because it's extremely, there's a lot of cases, and I don't have those nearly as good of a way to explain all the different cases as I do for insertion. Okay. So basically what we're going to do, I think I'm going to do it the other way, right? Let's show that a red-black, okay, so if it has internal nodes, n internal nodes, it has height at most 2 log n plus 1. So basically we want to show, here's how we kind of do it. We want to prove that for any node in the red-black tree, the number of nodes in the subtree, right? So we're going to flip the problem on its head. And what I mean by that is instead of doing it as n and 2 log n plus 1, h is less than or equal to this, what I'm going to do is I'm going to say, okay, let's do 2 to both sides to get rid of this, like, I guess we can divide h by 2, take 2 to both sides, so now we have n plus 1 needs to be bigger than 2 to the height, right? So we want to show that the number of nodes in the subtree of black height equals BH of X is equal to, or less than or equal to, 2 to the, or I'm sorry, is at least 2 to the black height of X minus 1. And so we're going to do this by induction, right? So in general, what we're going to do is we always want to do this kind of thing by induction. And you ask, why is induction the obvious thing here, right? And the answer is whenever you have a nice counter, like height or black height or something like that, you want to induct on that, okay? So let's look at a tree, a subtree with black height. Black height equals, say, 1 or 0 or something like that. So if the height is 1 or 0, then what are the possibilities for this tree, right? Let's actually just steal some nodes. I'm just stealing nodes here. Ignore what I'm doing. Okay, I like this best. Stealing nodes. Let's draw it. So here are the trees of height. Black height equals 0, right? If you have a node, a subtree with black height equals 0, then it's just a red node, right? If you have a tree of black height 1, here are the possible options. You can either have a black node, or, and of course here, this is not right, or you can have this, right? You can have a black node with 2 red children, or you can have a black node with 1 red child over here, or you can have a black node with 1 red child over here, right? Here's all the different options, cases. So here's our base case, right? And we just list out all the trees of black height X is less than or equal to 1, right? And now all we have to say is that is the number of nodes here equal or less than or equal to, oh, I'm sorry, greater than or equal to 2 to the black height minus 1? And the answer is, well, 2 to the black height minus 1 here, the black height here is 0, so 2 to the 0 is 1, 1 minus 1 is 0, so here 2 to the 0 minus 1 is equal to 0, so as it turns out the 1 node is bigger than or equal to that, so yep. And then let's do it again. So here, the number of nodes here is 1, which is bigger than or equal to 0. Okay, cool. And then here we would say, well, 3 nodes is definitely bigger than 0, so yes. And the same thing applies in all these other cases, right? 3 nodes, 3 nodes, 3 nodes. Right, so we always have more nodes than 2 to the black height minus 1, at least in the 0 and the 1 case, right? So I guess here we actually, we need to make this 2 to the 1 minus 1, so this needs to be at least 1 node, right? It needs to be at least 1, not 0. Sorry, but it doesn't affect it because the good news is that the math still works. Everything is still good. So the base case is done, right? Base case is done. Nice. So what have we shown, right? At this point, we haven't shown very much. All we've shown is that the number of nodes in a subtree is bigger than or equal to, like, a subtree defined at the node x is bigger than or equal to 2 to the black height of x minus 1. So what we're going to do is we're going to assume that, right, that's our inductive hypothesis. And so let's do our inductive hypothesis on this. And so what we're going to do here is we're going to say, okay, if we assume that that's true, right, assume this is true, then what we're going to do is let's look at something with a black height 1 greater. So let's assume that, you know, if we have black height of x, it's true for black height of x is less than or equal to, say, h, right? And so now let's look at a tree of black height of x is less than or equal to or is equal to h plus 1, right? And so now we get to look at this tree, and let's look at what happens, right? So the answer is, what do you know about a red-black tree? The answer is that if there's a bunch of different conditions, so the root is always black, and then let's steal some trees like this. So you can have something like this, right? So this is these are two red-black trees. So basically the point is that I'm going to assert that the root here of this subtree has to also be black. Just to kind of make a point, right? So there's right, so these roots of these trees are black, not red. Okay. So this is one possibility. Here's some other possibilities, right? The other possibilities are that you're actually in a condition more like this, and it's going to require a little bit more drawing out. But let me just do it. Here we are. Here's the other case, right? Now, technically, it's possible that... no, actually, I think... No, never mind. I think this has to be basically the case, right? So here are the two cases, right? Either we're in the case where this is true, right? Or we're in this case, right? Because this is also something where the black height is h plus 1, right? The black height is h plus 1 because when you count the black heights, this becomes h plus 1. And so this is, 1, 1, h, right? So h plus 1, h plus 1, h plus 1, h plus 1. So with all these extra red nodes, it actually makes it better for us, because remember that these trees all have to, by the inductive hypothesis, they all need to have the number of nodes in their subtrees has to be bigger than 2 to the black height minus 1. So there's at least 2 to the black height minus 1 nodes, right? At least that many here. And then there's at least that many here. And then we do our standard trick where we add this all together, right? We get, 2 to the black height of x. Let's just say 2 to the h minus 1 plus 2 to the h minus 1. And then you notice that we have a black root here, so we have to add 1, which gives us 2 times, right? 2 to the h minus 2 plus 1. And so this is our standard trick. Once you have 2 times 2 to the h, you get to write that as 2 to the h plus 1 minus 1. And then you say, oh, well, hey, that's the black height. So 2 to the black height of the new, root minus 1, like that. And then if we have the actual thing is we have to do the same thing here, but actually it's even better for us because we have what? We have 2 to the h minus 1. We have like 4 subtrees plus an additional 3 nodes, right? So in this case, it's actually equal to 4 times 2 to the h minus whatever. It's just going to end up being minus 1 overall, because it's going to be minus 4 plus 3. And so in the end, we're going to end up with 4 times 2 to the h. So actually, this doesn't turn out to be h plus 1. This turns out to be h plus 2. And so, as it turns out, that this is actually strictly bigger than the 2 to the black height minus 1, right? But remember what the thing we're trying to prove is. We're actually trying to prove that the nodes in the subtree are greater than or equal to. So here, it's equal. Here, it's greater by a factor of 2. So greater than is good, equal to is good. The only thing that wouldn't have been good would be less than, right? We just want these trees to be fat. Because if the trees are thin, right? If the trees are, I guess you wouldn't call them fat and thin. Generally, when a tree is mostly empty, you call it sparse, right? Autumnal or something. The point is that, all of its leaves are falling off or something. The point is that, a sparse tree, well, what we're trying to prove here is that the tree is not sparse. I think that's what I really want to say. because we're trying to prove that the number of nodes in the tree is bigger than a certain quantity that you calculate. And so the good news here is that that's true. So we're done, right? Now, so what we've shown is that the nodes in any red-black tree is equal to 2 to the black height, I'm sorry, not equal, is bigger than or equal to 2 to the black height minus 1. So here's the thing that we know, right? So now we want to argue, so this ends the induction. So the induction proof is done. But we still want to argue that this thing is all log. So how do we get that it's all log? So there's one last thing we have to say. Here's the last thing. The last thing we have to say is that any red-black tree has height at actual height, at most 2 times black height, right? And I'm going to say this, of course, what I want to say is proof. The answer is obvious. But I have a rule in life. Whenever I say something is obvious, that means not obvious. So it might be obvious, it might not be obvious, I don't know. So, okay, so any red-black tree has an actual height, at most 2 times black height. And so the reason why we want to say that is because what can happen, right? There's 2 options in every case. And you see that these are really the only 2 options. Either you get from h to h plus 1, either you get from black height h to black height h plus 1 by having a black parent of 2 black children, and that'll do it for you, or you can have a black parent of red children, which will increase the height, the actual height by 2, but it only increases the black height by 1. And so that fixes that causes, that kind of proves our statement, right? Any red-black tree has actual height. Basically what I'm saying is, like, either you have black children or red children. If black, then that increases the height and black height together. If red, then it doesn't increase the black height, but it does increase the actual height by 1. But then the children there must be black. So you can't just go on forever increasing the height of these things, right? You can't just have red nodes and red nodes and red nodes all the way down, because then that would violate the red-black tree property. Okay, so the last thing I'm going to do today in the lecture is we're not actually going to code it, because coding it is a bit scary, perhaps. But instead of that, what we're actually going to do is we are going to just do some visualization examples. I might talk about deletion next time and all that, but for now, let's just do some deletion, some examples, okay? So hopefully I get all this right, because even after I explain all the rules, sometimes it's still confusing. So let's insert 25, just to insert a number. Let's insert 75, right? Okay. And I'm not saying anything because you see that the root is black, the child is red. Okay. Now let's insert 101, okay? Let's insert, so it's going to insert as usual, right? And then here we're in a red-red condition, right? And then what do we do? So we see, aha, my parent is red, I am red. Problem. So since we're having a problem, what we're going to do is we look up to the grandparent and we say, grandparent, granny, grandpa, what's your other child? And they say, I don't have one. And so you say, okay, that means we're in the black uncle case, right? Because null pointers are considered to be black. And so what we're going to do is we're going to rotate. And remember that this is the black uncle straight line, right? So we're going to rotate against the imbalance. rotate against the imbalance, single rotate left, there we go. And then you notice we need to swap the colors. There we go. Okay, now let's insert 35 for no reason, other than I'm inserting 35. So here's 35, it goes in as usual. So what case is this, right? This, I tell you, and I'll just, here's the, you know, if you're interested. There it is. What do? Right? You say, I'm in the, here's me, my parent is red, so this is a problem. Grandpa, what's your other child? They say, red, and you say, oh goody, right? What you say is, this is the recoloring case. So you pull the color down, and this is fine, right? There's nothing wrong with this. If this were not the root, then we wouldn't be done, right? We'd have to shift up to the grandparent and then just keep redoing this. But since this is the root, we have to do one more thing. So this is the odd part about this case. We have to recolor this black. Normally you wouldn't do that, but in this case we're going to recolor it black because the root of the tree is red, colored black. There we go. If you ever find that the root of the tree is red, you color it black. And you notice that it really, I guess the question that I should ask is, does that matter? And the answer is yes and no, right? So maybe I'll put that on a homework and ask people to understand what all the things are going on. So, okay, so let's insert 52, right? Or let's insert 82, right? So that it goes into the right side. And so this, I think, is just going to go in, right? There we go. No problem. No violation. How about, you know, let's say 95, right? Let's insert 95 and see what happens. So, inserting 95, cool. So, good, this is a good example, right? And why is this a good example, you might ask? And the answer to that is, this is a what case? Right? Think about it here. So here's us, here's our parent, there's the red violation, right? So we have to look at our parent, we say, parent, you know, what color are you? And they say red, and we're like, no, that's not cool. So we got to do something about it. We ask grandparent, what's the color of what's uncle color, right? What's uncle color? Uncle doesn't exist, so uncle is black, right? And then we say, is this, so we know we're in the black uncle case. Is this the straight line case? No. This is the zigzag case, right? So the first thing that we do is we do the zigzag rotation, right? And let's see how this thing does it. It might do the recoloring and the rotations together. I forget exactly how this does it. So we're going to rotate first, single rotate. There we go. There's our rotation. And now we're going to rotate, so now we're in the black uncle, right? Now we're in this case where here's us, here's us. No, I'm sorry. We're still here. Parent is red, uncle is black. So now we do this rotation. And then finally, right, we have to flip the colors of the other two nodes. And so that fixes it. All right, so let's insert 135, right? So inserting 135. This is what kind of case is this, right? We look up here, we say, parent, you are? Parent says, I'm red. You're like, ah, God, not again, right? And then you say, okay, grandparent, what about your other kid? Also red. Cool. Here's what we get to do. We get to shift the black color down to these nodes, color this one red, and then the question is this a red-black tree, right? This looks kind of weird because at this level you have a black node, at this level you have a red node, but if you think about it, are all the black heights the same? The answer is 1, 2, 1, 2, 1, 1, 2, right? So all the black heights are 2 from the root, so the black heights are always constant. Now this is the node where we're at. We're right here, but the point is that when you look up, right? So this is the red uncle case. But now that we're done with the red uncle case, we switch to the grandparent and we ask, are you now the child of a red node? And the answer is nope. So you say we're done. All right, so let's insert another node. Let's insert, say, let's insert 150 just to see what happens. Haven't really thought through this one yet. I know it's a straight line case. I guess it's a... Right, so if we're here, this is just another black uncle straight line. So we'll just do a single rotation and then swap the colors. Right? So then you swap the colors. There you go. Okay, so now let's insert some stuff over on this side here. I want to get this tree to do some funky stuff. So let's insert, let's see, 77. This won't cause, I don't think this is going to cause anything to happen, right? And you might ask, well, why? And the answer is, well, I've inserted a red node. What if the parent is black, right? And you might say, well, I don't know what to do in that case. And the answer is you do nothing, right? You see that we haven't messed with any of the black heights. We haven't done anything bad. We're just inserting a new red node. It's fine. So now let's insert another red node. Okay, there we go. Let's insert another red node. Let's insert, say, 86. And again, this shouldn't do anything, right? All right, so now let's try to do something else. Let's insert 87 and see what happens. Or let's insert 85 and see what happens. So, okay, so where are we? We're at 85. Our parent is red, our uncle is red. So we pull down the color, right? Cool. Now what? Now what? So now we set ourselves to the grandparent. And this, I like this case. This was a good case. This is a great case. One of the best cases I've ever seen. And why is this so good? Because now we're at 82, right? Its parent is 95. We still see a violation. We have to do something. We go to the grandparent, who is the root, and we ask, what's your other color? We say, okay, you are, what are you? Wow, I'm looking at a black node. I'm like, what color are you? You are a black node. And so we're in the black uncle zigzag case, right? So we're in the 2B case, black uncle zigzag. And so what we do is we resolve the zigzag first. We'll rotate 82 up to be the root, right? We're going to rotate 82 this way, then we're going to rotate 82 this way. So that's how you resolve the zigzag case, both for an AVL tree and for a red-black tree. So let's do it. First we rotate, and then we rotate, right? So that's the zigzag rotation, just like for an AVL tree. And now you look at it and you say, okay, I forget what to do now, what, right? And then you say, right, what I have to do is have to fix some colors, because why do I have to fix the colors? Because the black height here is 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, right? 0, 1, 1, 0, 1, 2, 2, 0, 1, 2. So the black height is not correct, right? It doesn't work. But the good news is there is a simple exchange that you can do to fix it, and that exchange also recolors the root black. So it's going to do it all for us, right? We swap the color of this 75 with 82, and there we go, right? Okay. I think we've actually been through most of the cases. I think we've done zigzag, we've done the black uncle straight line, black uncle zigzag, and we've done the red uncle color exchange cases. And just remember that the red uncle color exchange has to be the one that keeps going. If you get to a rotation case, like even if you have to do the 2 rotations for the zigzag, you notice that this node is black now. So if this node had a parent, and that parent was red, I don't care, because I'm black. I'm good. If I had a black parent, I also don't care, because I'm black, right? There's no rules about, black parents having black children. They're totally allowed, right? Here we have this nice, nicely balanced tree. There's ways to... Deletion is a way to kind of create some more... If you just do insertions, these structures look really nicely uniform. If you do a bunch of deletions, you can kind of... Basically what you can do, the secret is you can actually kind of just delete all the red nodes out of a red-black tree, and because it doesn't affect the black height, you actually don't really have to do anything. So that's just incidentally, that's a fun fact. But yeah, maybe we'll talk about deletion next time. So you see how insertion works. And insertion basically works by, you ask yourself which of the 3 cases you're in. You're either in the red uncle case, or you're in the black uncle with straight line case, or you're in the black uncle with zigzag case. And whichever case you find yourselves in, you just do this, whatever that thing is, and you rebuild the tree. So basically, if you ask yourself, like, what kind of test questions am I going to write based on this kind of stuff? The answer is going to be, I will give you a red-black tree, and I will say, insert this node, and then show me the resulting tree, right? And so then you will have to do that. Or, I might even just ask you, like, part A, what case are we in? Part B, do the rotations or recolorings, right? And so, because it's good to be able to identify, and I know that there, if you say, well, identifying what case it's in is pointless because outside of this course, all the cases have different names, different numbers, all that stuff. So, it's totally useless knowledge. The answer is sort of, I think if you learn the red-black tree stuff well enough using these tricks, then you will be kind of, granted the probability that you'll ever actually implement a red-black tree is, probably 0.1%. But on the other hand, that's how it is. Okay, so I will let everybody go. I hope this was a good lecture on red-black insertion. I actually, my opinion is that it was. I thought it did okay. Hopefully it was understandable. I'm going to try to make test questions where it's something that you can think about and do, and something that's not too impossible. But anyway, yeah, so red-black insertion is actually, if you think about it the way that I've kind of taught you here, and I actually only discovered all of these tricks in the past, while teaching it. When I learned all this stuff, basically it was just fed to me as, here's case 1, here's case 2, here's case 3. And I didn't really have a good model in my head of how to think about it. It was all kind of random. But you see that it's actually not so random. What it is either you're going to do an AVL rotation, and then you're going to fix up the coloring, or you're just going to fix the coloring and then just go up to the grandparent, and then go again, right? So that's basically it. I say go ahead and, the way to study for the next exam on AVL and red-black is to actually play with this thing, and just keep inserting stuff and deleting stuff, and of course we haven't done deletion yet, but keep doing that until you're, able to watch it and predict it, right? So the kind of, basically the game that I was just playing, right? I say, I'm going to insert this node. And so you just, you insert it like you do, step forward through it until it's in the right place, just like a binary search tree. I assume you can all do the binary search tree insert. And then think about, don't hit the forward until you've thought about it, and come up with an answer, and then hit it and see what happens. And if you're right, then you're going to be in luck, and if you're wrong, then step back and see why you're wrong. See what happened, right? That's the important thing. Learn from don't just be like, oh, that was just a mistake. go back and learn from why you guessed wrong, right? And the answer is a lot of times you get confused about where you are. Like, I think that's 98.9% of the confusion. It's just you'll think you're here, but you're actually here, and so the uncle is, you know, if you're here, then the uncle is red, and if you're here, then the uncle is black, so you might misidentify the case that you're in. But anyway, okay, I'm going to let everybody go, and then I'm going to be around on Discord to help out with the project, so, you know, that's how it goes. So I'll see you all there. I'm sure you're all very excited. Very excited. All right. Talk to you later.